we have two examples where we can use the loop rule. So the first one, it's your turn, so I do encourage you to pause the video and try it on your own. And let's take a look at it. It said, find the sum of the potential differences across all elements of the circuit. So there's two ways to go about this problem. One way is to do some math and figure it out, which is totally fine. The other way is to not do any math and just think about what the loop rule just said. All right, go back to what the loop rule just said. It said the sum of all potential differences across our closed loop. This is a closed loop here as we go around it. The sum of all of those potential differences, some are positive, some are negative. When you add them all up, you get 0. That's what the loop rule says. So without doing any math, we already know that the answer is 0. But I like this example because I do like to show the math because we need to know how to do this. Because usually one of these variables is going to be an unknown. So we have to be able to set up the equation so that we can solve for the unknown. So the way that we use the loop rule is you start anywhere in your loop. My preference is to start at the negative terminal of a battery. It's just a personal preference. And I usually put a little star there to show I'm starting there. So first you pick a starting point. Number 2, you pick what direction do you want to go, clockwise or counterclockwise. It doesn't matter, but I like to label it. Whatever I choose, I'm going to go clockwise. So I'm going to label that I'm going to go clockwise. Okay, I got my starting point. I'm going to go clockwise across each element one at a time and think about how much potential is lost or gained as I go across each element. So first thing is I'm going down through this battery from the negative to the positive terminal. We just learned that that means you're going to gain voltage. So we're going to have plus 10 volts here. Okay, keep going. Now we're going across this resistor to the left since we're going clockwise. But the current that was given in the problem is going the opposite direction. So go back to the rules. If you cross a resistor opposite the current, that is also a gain in potential, a voltage gain. And the amount of voltage gained is IR, right? It's always plus or minus IR, depending on the direction of the current. So in this case, it's going to be a positive IR. The current is 2, and the resistance is 3. So it's going to be a positive 6 volts as you go across this resistor. Keep going. We're going upward across the 6 ohm resistor. Once again, we're going against the current. That's going to be another gain. Plus IR. I is 2, resistance is 6, so plus 12 volts for this one. Almost done. Now we're going to the right across this battery, but we're going from the positive terminal to the negative terminal. That is a loss. So I just want to give you time to think about it. That's a loss when you go to the negative terminal. So minus 30 volts as we go across this battery. And finally, we're going to the right across the 1 ohm resistor against the current. That's going to be a gain. Plus I, which is 2, times R, which is 1, plus 2 volts. So we have all of our voltages across each element. The loop rule says that when you add them all up, they should equal 0. Well, let's take a look. We have 10 volts, plus 6, plus 12, minus 30, plus 2, and you can see that's 28 minus 30 plus 2. That does equal 0 volts. So this is a really good example of putting that loop rule into action. Let's do one more, and hopefully you can do more of this one by yourself. So this problem is asking us for the current through the 3 ohm resistor. Pause the video, use the loop rule, pick a starting point, add up all of your potential differences, sum them up to 0, and that will let you find your unknown. Okay, let's give it a shot. Pick your starting point, I'm starting at this negative terminal. Doesn't matter where you start. Pick the direction that you want to go around your loop. I'm going to pick clockwise. Again, doesn't matter the direction that you pick. And now go across your elements. So we're going from a negative terminal to a positive terminal. That's a gain. So plus 9. And then we're going here. Now, are we going with or against the current? There's no current labeled. So that's one thing that you have to do when using the loop rule. If the current has not been labeled, you must label the current. Pick any direction for the current, but be consistent. So you can pick the current to be going clockwise or counterclockwise. It doesn't matter. Be consistent. I'm going to pick the current to also be going clockwise. So the current is going to go to the right through our resistor. So as I'm going across my resistor, I'm going to the right in the same direction as the current. So it's going to be a drop minus I times R. Minus I, we don't know what the current is, but the resistor is 3, minus I times 3. And then we go across this 6-volt battery. We're going from a positive terminal to a negative terminal. Is that a drop or a gain? That is going to be a drop because we're going from a high voltage to a low voltage. So minus 6 volts. And then we're back to where we started. We know that once we've added up all of these are delta V's, that the sum is 0. So you see how useful this rule is. It will allow us to solve for the current. That's the only unknown in this equation. What we end up having is 3 equals 3 times I if we move the I times 3 to the other side and do 9 minus 6. If we solve for I, we get 1 amp. So that is the current. Now you probably have a few questions such as, well, how did you know to pick the current that way? I didn't. I mean, technically I did. But let's pretend I didn't. Let's say that I thought the current was the other way. Okay? So let's say I had thought it was this way. As long as you're consistent, then no problem. The direction of the current only matters through the resistor, right? Because when you're looking at the batteries, we don't care about which way the current's going. We're only caring about the terminals. Are you going from low to high or high to low? So if you had labeled the current to go to the left and you still wanted to go around your circuit clockwise like we did, what would be the difference? The 9 volt would be the same. You're still going from the negative to the positive. So you'd have a 9 volt. But now you'd be going against the current here. So that would be a gain. That would be plus I3. And then you would still lose 6 volts over here. And the sum would still equal 0. Oh, I forgot the 3 here. There we go. When you solve for I here, you're actually going to get negative 1 amp instead of positive 1 amp. So the trick, and we'll do a lot more of this in the next video, the trick is it doesn't matter which way that you label the current as long as you're consistent. If there was another resistor over here and you said that the current was going to the left, then the current would have to go to the right here. It has to follow a continuous path. That's what I mean by being consistent with the direction of the current. So as long as you're consistent, when you get your final answer, if the final answer for your current is negative, all that means is that you picked the current to be in the wrong direction. So when we picked the current to go this way, the current was negative. That just means that it actually was going the other way, but it still has that same magnitude. It's still a 1 amp current. That negative tells us we picked it the wrong way, and so now we know the current actually flows clockwise in the circuit. This makes sense because the 9-volt battery is more powerful than the 6-volt battery, so it's going to force the current to go clockwise. But, whoops, microphone drop there, mic drop. You don't have to think about all of that because if you guess the wrong direction for the current, your answer will come out negative, and that will tell you exactly which way the current went.